Welcome to Engineering Studio with Dr. Mohammad Tahir. In this video, we are going to discuss about the types of buckling, elastic buckling and inelastic buckling. We will also study the types of column based on the buckling behavior. Overall buckling behavior mean long column, short column and intermediate column. We will also study the type of column based on the local instability, compact section, non-compact section and slender sections. So first of all, elastic buckling. So if buckling of column occurs without the yielding of section and the section is in elastic range, then it is termed as elastic buckling. Upon removal of load, member will regain its original shape. So in case of elastic buckling, column section will not yield and it will remain within the elastic range, and upon the removal of load, the material will gain its original shape, or the section will gain its original shape. So long compression members fail by elastic buckling. There will be no inelastic buckling, or we can say there will not be any yielding. In case of short compression members, there may be yielding of the member and even it can go into the strain hardening range. So in case of short columns, we can go up to yield as well as in the strain hardening range. So we can go up to the ultimate or strain hardening range in case of short compression members. But in case of long columns, we will have elastic buckling. The material will not reach up to its yield stress. So next is how we can calculate the elastic buckling load. So we can calculate the elastic buckling load and elastic buckling stress by using Euler's buckling formula. So critical load is given by pi square EI over KL square, critical buckling load. So we can find the critical buckling load by using this formula. This is given by Euler's. And if we write this I in terms of AR square, so we can write pi square E AR square KL over R square. So again, if we rearrange in such a way that we take this R in the denominator, so it will become pi square EA over KL over R square. So this term KL over R square is slenderness ratio. So we can see here the critical buckling load is directly proportional to the elastic modulus of the section, area of the section, and it's inversely proportional to the square of slenderness ratio. So for members with larger slenderness ratio, critical buckling load will be smaller. If we want to convert this critical buckling load into elastic stress, so we can write sigma is equal to P over A, or we can write P is equal to sigma into A. So P is equal to sigma or stress Fe into A. So we can substitute this PCR. So here we will have Fe into A into here we will have A. So A will be cancelled out on both sides. So we will left with Fe is equal to pi square E over KL over R square. So from this equation we can get the elastic buckling stress. So this is critical buckling load and this is corresponding stress value. So if we see this stress is inversely proportional to the square root of slenderness ratio. For members or for sections, for columns with larger slenderness ratio more than the specified value, we will have stress in the elastic range, but as we keep on decreasing this slenderness ratio, the stress will continue to increase and it can reach up to the yield strength. So it is important to note that the buckling load determined from the Euler's equation is independent of strength of steel. So it is independent of Fy. So we do not use the strength of steel, we only use elastic modulus and slenderness ratio. So the most important factor which this load depends is the KL over R, slenderness ratio. The Euler's buckling load is inversely proportional to the square of the slenderness ratio. So with increase in slenderness ratio, buckling strength of the column drastically reduces. So as we go on increasing the R value, the stress value will continue to decrease and vice versa. So next is inelastic buckling. So if we have a section such that it buckles but some of its part undergoes yielding, so then we say it is a inelastic buckling. So in usual situation, failure occurs by buckling after a portion of cross section has yielded. So in case of elastic buckling, the complete section remain within the elastic range, but in case of inelastic buckling, some part of the section, for example it is a C section or W section, some part of it will yield. The remaining part will buckle, but some part at some local position it will yield. So we say it is a inelastic buckling. So in that case, the material will not recover its original shape. So some deformation will stay there, will remain there. So this is known as inelastic buckling. So this variation in column behavior with change in slenderness ratio is shown in figure. So this figure shows the variation of strength in stress in the column section with the increasing slenderness ratio. So when we have very short slenderness ratio or very small slenderness ratio, so we term it as a short column, and in that case the stress in the column can reach up to the yield strength. As we go on increasing the slenderness ratio, when it is between 30 and RC in the critical slenderness ratio, so in that case we will have inelastic range, or we will have inelastic buckling. So column will buckle, but some of its portion will yield. So we can say it is a inelastic buckling. And if the slenderness ratio is more than this RC value, so in that case we will have elastic buckling. So material will not reach its yield stress at any point. So between this range RC and 200 we will have elastic buckling, and between 30 and RC critical slenderness ratio we will have inelastic buckling, and if the slenderness ratio is less than 30, so we will have yielding of the section, complete yielding of the section. So this RC critical slenderness ratio can be calculated by using this formula. RC is equal to 4.71 square root E over Fy. So for A36 steel with Fy is equal to 250, this RC value is 133. So for sections made up of A36 steel, if the slenderness ratio is more than 133, it will have elastic buckling, but if it is less than 133, it will have inelastic buckling.